Hi everyone, welcome back to Dave's Math Channel. This is my seventh video in my sub-series on integration and my series on um, first year calculus. Today I'm going to talk about a special type of substitution, namely trigonometric substitution. Sometimes people just call trig substitution. And this is where you want to substitute an angle for your variable of integration. And anyway, this is just kind of a picture of what's going on. So there's sort of three different examples here of where you might want to make a trig substitution. If your integrand has an expression of the form a squared minus x squared, square root of a squared minus x squared, you want to make that go to a cosine theta. So you let x equal a sine theta in that case. If you have square root of a squared plus x squared, you want to let that be a secant theta, and then you let x, so then x is a tan. This just comes from trigonometry. So basically the idea is you want to let x be a simple trigonometric function, maybe multiplied by a constant, in this case a, where you have a squared plus or minus x squared. And then this expression that you want to simplify, then the integrand, turns into a nice trig function. So you'll see a bunch of examples. Here's a simple example. So suppose your integral was square root of 9 minus x squared over x squared dx. Well, then if you let x be, in this case, a is 3, so you let x be 3 sine theta, then the numerator becomes 3 cosine theta. X squared is 9 sine squared theta. Um, and dx is going to be 3 cosine theta d theta. So when you simplify all this, you're going to get minus cosine theta plus theta. I'll go over more examples like this, but this is the idea. Anyway, here this is kind of this table summarizes more of what you want to do. So when you have, if you see square root of a squared minus x squared in your integral, then you want to make the substitution x equals a sine theta. And then dx will become a cosine theta d theta, and square root of a squared minus x squared becomes a cosine theta. And similarly, if you see square root of a squared plus x squared, you want to let x equal a tan theta, and then dx is a secant squared theta d theta. That's just derivative tangent, and square root of a squared plus x squared is a secant theta. And in the third example, where you see square root of a x squared minus a squared, you let x equal a secant theta, and then dx becomes a secant theta tan theta d theta, and square root of x squared minus a squared becomes a tan theta. So if you make those substitutions, your integral will simplify considerably and usually can solve it. So I'll just do a couple examples here. You can do tons of examples of this, but I'm going to do a couple sort of simple ones. So let's first look at this example. The integral, this is a definite integral. I'm going to do two definite integrals today. So the integral we're starting with is the integral from 0 to 1, definite integral of x dx over square root of 1 minus x squared. Well, in this case, a is 1, and we want to just let x equal sine theta. So what happens when we do that? Well, 1 minus x squared, square root of 1 minus x squared in this case is cosine theta. So the denominator becomes cosine theta. X was sine theta, dx is cosine theta d theta. So now the integrand becomes sine theta cosine theta d theta over cosine theta. Well, you notice that you can cancel the cosine thetas in the numerator and denominator. You're just left with the integral of sine theta d theta, theta going from 0 to pi over 2. The other thing I forgot to mention is you have to change your limits of integration, because whenever you have to do that whenever you make a substitution in a definite integral. In this case, our original value variable was x, and we let x be sine theta. So we're substituting for the theta now. Theta is the arcsine of x, and the arcsine of 0 is 0. Arcsine of 1 is pi over 2. So now our integration limits become 0 and pi over 2. And so we're integrating from 0 to pi over 2 sine theta d theta. This is a very easy integral. The integral of sine theta is just minus cosine theta, and we're evaluating from 0 to pi over 2. And I think I mentioned a couple of videos ago that whenever you have cosine, you usually want to switch the limits around. That'll get rid of the minus sign. So it's just cosine theta evaluated from pi over 2 to 0. That's cosine of 0 minus cosine of pi over 2. Cosine of 0 is 1, and cosine of pi over 2 is 0. So the answer is 1. Pretty simple. And let's do a harder example. This one's actually pretty hard, but I think you'll get used to this the more you do. So actually, I think this is a nice example. So here we're asked to integrate the square root of a squared minus x squared, x going from 0 to a. And why is this interesting? I think I gave this example before when I was going over numerical integration. When we were doing Simpson's rule. I don't know if you remember this, but y equals square root of a squared minus x squared. You can rewrite that as x squared plus y squared equals a squared. That's just the equation of a circle of radius a. But we're only getting a quarter circle here because we're only going from 0 to a, so we're in the first quadrant. Remember, when actually y equals square root of a squared minus x squared is just the upper semicircle. So we're really only doing the upper half plane, but then we're also only doing the right half plane because we're integrating from 0 to a. So we got the quarter circle in the first quadrant. You know that the answer should be pi a squared over 4 because the area of the whole circle is pi a squared. So let's see if that's what we get. Like I said, this example is pretty complicated, but let's just go through it. So we know that we have to use the substitution x equals a sine theta again for this example. So, and that means the square root of a squared minus x squared is going to become a cosine theta, and also dx is a cosine theta d theta. So when we're done with everything, we get a cosine theta twice, so we're going to get a squared cosine squared theta. And when again, we have to change the limits of integration to limits on theta. Theta is going from 0 to pi over 2 now. And like I said, this is a quarter circle. So the angle is going from 0 to pi over 2. And then we can factor out a squared because that's just a constant. So now we have to integrate the cosine squared. And how do we do that? I mean, well, there's a trick you can use. You can use a trigonometric identity. There's two very useful trigonometric identities you can use. You'll see this a lot when you do integrals. You'll see cosine squared and sine squared, or you'll see even powers of cosine and sine. Whenever you see that, you can use these two identities here. And it turns out that sine squared theta is 1 minus cosine 2 theta all over 2. And cosine squared theta is 1 plus cosine 2 theta over 2. Those are two very useful identities. You use them a lot when you do this kind of stuff. So now we still have to evaluate this integral. Yeah, it looks like I left out a squared here. Don't worry about that right now. Yeah, I made a mistake on this slide. Everything on the left side should be multiplied by a squared. Sorry about that. But anyway, we want to evaluate this integral of cosine squared. Cosine squared, we're using this identity now. Cosine squared theta is 1 plus cosine of 2 theta all over 2, so we can factor out 1/2. And then we just get the integral of 1 plus cosine 2 theta, theta going from 0 to pi over 2. And remember, you can always break up, since integration is linear, whenever you're integrating a sum, that's just a sum of integrals. So the integral of 1 d theta, which you can also write as the integral of d theta, that's just going to give you theta evaluated between 0 and pi over 2. That's just pi over 2. So on the left, we're going to get pi over 4 because we're multiplying by 1/2. But then we also have to add 1/2 the integral of cosine 2 theta. And I'm going to call that integral j. So j is the integral of from 0 to pi over 2 of cosine of 2 theta d theta. Well, that's actually a pretty easy integral. We have to use another substitution to do it, though. So what do? We define another angle we call phi. We let phi be 2 theta, so that theta is really phi over 2, and d theta is d phi over 2. So when you make that substitution, j, this is what I'm calling this integral here, this becomes 1/2. We can factor out the 1/2, and then we just have the integral of cosine phi d phi, but remember that we have to change our integration limits to limits on phi. since phi is 2 theta, these limits are now 0 to pi. So this is just, we know what the integral of cosine phi is. It's just sine phi. So we're evaluating 1/2 sine phi, phi going from 0 to pi. That's just 1/2 times sine of 0, or sine of pi minus sine of 0. You may remember from trigonometry that sine of pi is 0, and so is sine of 0. So you're going to get 0. J is 0. That means that, and like I said, I made a mistake on this third slide. Everything should be, on the left, should be multiplied by a squared. So the answer you're going to get is pi a squared over 4 plus j over 2. But we just said j was 0, so the answer is pi a squared over 4. So that's what we expected. It's the area of a quarter circle of radius a. So like I said, this was a more complicated example. But, usually when you do these trig substitutions, they're usually straightforward. Sometimes they involve a lot of work, but they're usually at least straightforward to integrate. It gives you a very good simplification of your integrand when you do these trig substitutions. So it is a very useful trick. Anyway, that concludes my video for today. Thank you for watching. Long live math, and I'll see you guys next time. Bye.